minus, but here it's showing you it's already got the linkage here. Right? So trigonal carbon to tetrahedral carbon. We're going towards a covalent intermediate here because this is from the lysine. Right? A base on the enzyme abstracts a proton from that lysine, from that NH2 at the end of the lysine. And then we pick up a proton from solvent here to release water and generate this intermediate. Okay? And this intermediate is called a protonated shift base. Okay? And that's a very important structure in biochemical reactions generally. Okay? So protonated shift base is a lysine side chain on the enzyme linked to a carbon on some metabolite. In this case, it's C2 of this glycolytic metabolite. So here we've got the carbon-carbon bond cleavage step, releasing a product here, glyceraldehyde 3-phosphate, and forming a covalent enzyme intermediate, which is called an enamine. It's called an enamine at this point. So this is a shift base. This is an enamine. This is the cleavage reaction. And now we've got the whole enzyme here linked to half of what used to be the substrate. Kind of looks like chymotrypsin in a way. Doesn't look like it, but right? Chymotrypsin, the enzyme goes through an acyl enzyme intermediate after half the substrate was cleaved away and diffused off. But the enzyme's stuck there with half the substrate covalently bound to it, right? The acyl enzyme in chymo. Well, here's the covalent enzyme intermediate in aldolase. In this case, it's an enamine. Okay? So what this mechanism is not showing you is, where's the carbanion? Where's the resonance stabilization? Because that's the secret of why it's possible anyway. And your authors unhelpfully do not provide that. So you can just look at this. Right, so we've got the shift base, right, from the lysine, right? And here's a base that's going to pick up this proton right here. Okay, so this is going to go there's a carbanion, right? This B here picks up the proton, right? Plus, right? And this is the product. This is glyceraldehyde 3-phosphate. Right? This is product 1. Okay. Product number 2 is stuck on here, right? So this then can go to this. Right, so this is the resonance, right, because we have this structure here. Right? Yeah.
In the boxed area,
Yes.
is that middle CH2OH? Is that correct?
I think so.
Okay. Not just CH?
No, that middle CH, that's middle CHOH is this. And this part is turned into glyceraldehyde 3-phosphate.
You just have extra
I think
hydrogen.
he's saying that you have to need hydrogen.
Did I?
Yeah.
Oh, I'm sorry, it should be CHOH. That's what you. Okay. So, right, if you draw it, the book. So what the textbook doesn't do is it doesn't show you this little minus here, right? And then so it doesn't show you that this has to form first, right? As this bond breaks, this is the breakage of the bond right here. As this bond breaks, you're building up negative charge here, right? But immediately it's got a place to go. It can go here, right? Because this N plus is an electron sink, right? That plus is like, I can accommodate a carbanion at C3 right after, as I cleave the bond, because I've got a place to put that negative charge immediately, sink it into that N plus. And where did I get that N plus? I formed a covalent bond with the enzyme lysine in the active site. kicking out water in the process. Yeah.
How long have we been aware of this level of detail of these mechanisms?
Some decades,
Okay.
2, 3,
So
4
then it's a
decades, depending on
difference.
which enzyme.
Does
Chymo was worked out in the 60s and 70s, one of the first. Aldolase was probably worked out in the 80s.
Yeah. I took the first part of biochemistry in a different school.
Yeah.
So they had me detail glycolysis down to the electron, but none of this was on it.
Okay, so the last part of it is the same as the first part, except now we're adding water in. Okay, so we'll go into that a little bit more on Monday and finish up.